Well, hello. I am going to talk about how to do this question called binary tree cameras. And I really like this problem. I don't know about you, but I'm a beginner and this is like it was fun, challenging, and it's solvable. And then I had a big inspiration from Mikhail Dekterev. Well, I mean, may have just copied his entire code. I mean, I didn't really copy it, but it was almost exactly the same. And yeah, he was very inspiring. So he was my muse, and I also like like I mean I wanted to like keep this for my own memories because it was really fun. And it took me like I don't know half an hour, but that's because I also checked the solution before I started. And so Mikhail, he used like a recursive. When I saw it, I was like, oh, it looks like a recursive solution. Um, I saw the root, like the base case root none return 0. I was like, yeah, I just write myself a recursive solution, and then recursive function. And if you don't know, like class just means you're making a robot. So class solution is like, oh, we're gonna make like robots or drones this way. So every single robot of class solution is gonna look like it's gonna have an arm called an arm, a wing, or whatever. It has a function. It's called a min camera cover, which means, oh, I forgot the question. The question says, if we have this like tree, right, these nodes, cameras can look at itself, its parents, or its immediate children. So we have it represented in the list formula. So 0, 0, null, because there's nothing here, then 0, 0, or like 0, 0, no, 0, no, 0, no, no, 0, like kind of like that, no, 0, yeah. So then you see, um, so that's how this question works. And immediately I thought, okay, let's just go on. Let's just like not think. Let's just go in and make it into a checkerboard. Because like I looked at these examples, it kind of looked like a checkerboard pattern. So I was like, okay, let's make it a checkerboard pattern. Let's start with we gotta do something. So we're gonna put in a camera in the first node, and then get on left, and then run on right. So, in a recursive function, like say this box represents everything that represents in the function, and we just put +1 to represent that we have a camera in here, and then we run, so running is represented by my rabbits, because you run like a rabbit, so you run on left, and then you run like a rabbit on the right side. And of course, whenever you run, it's going to do the same thing again, so of course you can see how it's going to trickle down. And so now we have it. Now that we've done the first node, we want to do the second node. And we want it to run like a rabbit on left and right as usual, so we're not touching that. But however, we want this to be whitened out. So it was black here, so we want it to be white here. And so how are we going to do that? So we're going to put an if statement. Put an if statement. So if it has something in the parent, then we're just not gonna have a +1. It's gonna be no cameras in there. It's gonna be white. It's gonna be devoid of surveillance, because it already has surveillance in the parent node. We don't want no surveillance here. I gotta have a okay. So if we were to continue this checkerboard pattern, so this will become a check. By this logic, it'll become like a checkerboard pattern. So if there's something in the parent, then it'll be white. If there's nothing in the parent, then it'll be black. So it'll just be like white, black, like going down from like the granddaddy to the parent to the child. So, and then of course it'll choose the most optimal, because like this is a very nice. So whenever you want a minimum solution, just run the result. You want to assign back the minimum of the result with something else. So you always want to do minimum result of something else and assign it back to the result. So this is how programming kind of works. And then we want to, okay, so this is an edge case. Not sure if we jump to the edge case right now, but oh yeah, we had to first talk about since when we do a checkerboard, we need to cover all our bases. So we need to make sure we do it when the first node is white. So we start white, then we do black, and so on. So when the granddaddy is white, and then your parent is black, and then the children are white again. This is how we're gonna implement it. We're gonna put like if let's say if it has no parent, okay, so it is the granddaddy. Then we also want to make sure that it's the first node, like the first node, and then we would make sure that so I can see myself being influenced after seeing someone else's code, because this is just like seriously, like I don't know if anyway, just look at this logic here, because it'd be like if it's a first node, this would be kind of my own logic. So if it's a first node, then I will push it down. It's also Mikhail's logic when he talks about forcing things down. But for me, when I approach it, if you just look at someone else's code, it's kind of hard to know what's happening. So it's pretty much impossible. So I think the best way to reverse engineer is always just to come up with your own solution, and then just be like, oh shoot, I'm stuck. What am I gonna do now? So that kind of stuff. And so then, so in my case, I'm still doing like the checkerboard, not so perfect solution. So I have to make sure the first node is whiter now, and so we don't have a +1 here. We get left, get right, and then we say that it's no longer the first node for the left and right. We say that it has nothing in the parent, so false, false. So that's how we do it. So then we would be like, okay, if we forced it down, like this is kind of a forcing down move. I didn't make up this term that he did. He called it the force parameter. I don't even have a force parameter in here, but you know how it is. So this is the node. So if there's only a single node, we will have to keep it in a node. So we have to make sure that in this edge case scenario, that if there is nothing, then we're not going to push it out. We're not going to push the camera out. If there's no left or right, we're not going to push the camera out for the first node. All right, for the first node, if there's nothing, we will only do the statement if there is a left or right. For the first node, you need to have left or right in order to do the statement. So that just covers that edge case, because we don't want to push the camera out of this node if there's just one single node. So then, like, I think part of the problem with solving it by hand without without being able to run it once and just get it right on the first try is to be able to know when you've hit all the edge cases. So when you hit here, I think if it were me, I would have been very happy, and I did run it, I did crash, and I was like, oh no, what did I do wrong? So I then realized that I was completely stupid. I was completely asinine, and oh, I'm sorry if you're a little kid, but it means I was a complete idiot. And maybe it's not a checkerboard problem, it's more like, where you have two white sandwiched by two black nodes, so you can have like a black, white, white, black kind of configuration. So then I realized that, okay, I now understand why, like, instead of like why there's a parameter called force within Mikhail's solution. And I also, like, I skipping ahead, I also saw that he had something different. Like, he did not do what I did here. He did left and did right. So I knew that there was some, like, nobody does something extra for no reason. Like, there was probably some no one adds in logic for no reason. There's probably some other edge solution. So now, anyway, I looked at this. I knew I had to force this down, so I had to let this be treated like a first node again. right? I have to give him what Mikhail calls it, the force parameter. And then, so I have to, treat, so how do I reach this node? First, how do I reach this node here? When we call this function on this node, so its granddaddy has a camera. Its granddaddy is black. All right. So then when we go back to the granddaddy, let's say, okay, right here, let's go to the parent. So then if we go in the parent, if this guy when he runs this conditional statement, if in parent, because his parent, the granddaddy, is black, so this parent will be this code is where you want to modify, because this guy is the parent of the node you're looking at. Your parent, this guy's your parent, so you have to think how he's gonna affect you. So then you get root left, get root right. So then we know that, okay, we have to make this into a new first node. So we have to be like parameter this has to be true again. So that's what we do. We make it true. And then we look at the edge cases, another edge case. So this kind of be the very popular edge case. It's not just in math, it's also like in biology, all these turning points. So all these turning points. So you can see when you think about it, you can't just force, like when I made an assumption that you can just force the camera down into both left and right, of course that's gonna be wrong. And then whenever you make an assumption, you should write it down and be like, oh, I need to come back to this and fix it, because assumptions tend to not be right. And so then I basically have to split it left. So if I were to go down the left route and to give this guy a camera, then I would have to force on the right side. So I'm gonna be doing something like that. Go on the left. So left is normal again. It's just treated normally. Like, it just gets a camera. It doesn't get all the force down that the first node gets. And then the right is treated like it still has a force parameter. It's still treated like a first node. So you can see that it can be pushed down here. Can be pushed down, and that's on the right side. That's what we want, because we don't want this. We don't want we want to have just 2 cameras covering this. We don't want to have 3 cameras covering this. So as you can see, that's optimal, because we want to have 2 whites between 2 blacks. That's a very best case situation that you have to think about the best case always. Like, yeah, you can approach it as, a checkerboard or whatever, like close to best case scenario, but in the end you still have to, make the leap, make it stretch there. And then of course, I ran it again, super hyped up. And then I hit something and I was like, oh, that's what he meant by function tools. I was like, this is very cute. I was like, oh, it's gonna have to make a memo for each of these functions right here. So it's able to cache the functional arguments and the result. That's amazing. It can cache this functional argument. So it's a dictionary as usual. Dictionary just like a 1-to-1 mapping. So like A would be to 1, B would be to 2, that kind of mapping. And then the dictionary, it says right here is a memo, and a memo is like, you record stuff, data into a place where you can retrieve, so you don't have to do the same calculation again. If you ever have the same, like, say if I was to get anyways, if this tree was larger and I was to get something that looked like this again, then I can just be like, oh, I already know the result for this, or something. I can already know the result for this thing. If this is a part of a larger tree and I had the parameters for this node, I can easily just, like, instead of redoing this computation over and over again, I can easily just get the result from this node. So this is what memo does. It helps you keep track of things. All right, so let's just run it. So this is the code. When you run it, let's see how fast it is. So it's 120 milliseconds. Yeah, so that's pretty cool. I'm gonna go do another problem then.